Alright, in lesson 3 I'm going to be doing the same example that I did yesterday or in lesson 2, which was a 1D conduction heat transfer, except for today I'm going to add some heat generation. So if you remember from lesson 2, we had a rectangle in sizes of 10 and here and 5 in the vertical length. K or conduction coefficient was 100. Oh my, let me do it. Okay, it was 100, and temperature here was 100, and temperature here was 20. And that was what I did yesterday, and the Q was 100 times 80, which is the difference in temperatures, over 10, which is the length in x direction. This was our x direction, which turned out to be 800. Now what I'm going to be doing today is I'm going to show you how to add some heat generation in a 1D conduction. So I'm going to add some heat generation of let's say 2000 from bottom. So some heat flux or heat generation or heat is going to enter our rectangle from the bottom with 2000 units, and all the properties of a material in terms of conduction coefficient and temperatures on the left and right are going to be the same. And what you will see is the change in the vector of heat transfer. Yesterday the heat transfer was parallel to x direction, but today with this heat generation in here, we're going to have some shift in the direction of heat flux vectors. So with that, let's go to ANSYS and do the analysis. Okay, we're in ANSYS, and I'm going to start my analysis in here. Click Preferences and make sure that I'm going with thermal. I click OK, and then go to preprocessor and add an element. Like yesterday, I'm going to pick quadratic 8 node, click OK. Options, again, I'm going to stick with the default, so OK this one. And there's not going to be any real constants for the element that I picked, so I'm going to jump to the materials, material models, thermal, conductivity, and the conductivity or conduction coefficient, I'm going to give 100 again. Close this window and go to modeling. Today, instead of going through just simply making a rectangle, which is very easy, I'm going to go with steps by steps. I'm going to make some key points in active CS. The first key point at 0.000. The second one at x equals 10 and y equals 0. 1 and 2. The third one I'm going to put at y equals 5. And the fourth key point is going to be at x equals 0 at 5 equals 5, or y equals 5. And then I'm going to create 4 lines, straight lines from here to here. Click OK, and then create an area arbitrary by lines. So I'm going to pick 1, 2, 3, 4, click OK, and my area is generated just like what I did yesterday. Yes, or in lesson 2, I just came to this area and picked rectangle and gave the 2 dimensions, and then my rectangle was generated. Today, in this example, I just wanted to show you how you can go with defining key points and then lines and then areas and go from there. And then again, like yesterday or the previous lesson, I need to do meshing. I'm going to try a new meshing technique. I'm going to pick mesh tools in here today and go with smart size, pick smart size 3 and mesh areas. Click my area, click OK, and now the mesh is generated. So this meshing is kind of like automatic or smart meshing compared to the meshing that I did in lesson 2, which was manual. So I picked the size of the number of divisions per line manually and then meshed my area. They're both the same, or meshing is dependent on what you need from your analysis. Both of this could work. Here you see the number of elements that I have for this sample are more than the number of elements I had for my same model yesterday or in lesson 2, because I changed the number of divisions in smart size to 3, which is or I made it a little bit finer meshing. Now again, I have to go to load, come here, make sure I'm going with a steady state analysis. I'm going to close this window. Okay. Come to define loads, apply thermal. I'm going to apply temperature of 100 on the line on the left, apply, and a temperature of 20 on the line on the right. So far everything is exactly similar to the model in lesson 2, but here I'm going to add a heat generation on the line bottom. I'm going to say heat generation of 2000 from the bottom. And the other thing I want to do is I want to say that heat flux on the line on top is 0, which means no heat is flowing out of the rectangle from the top line. So my model is ready. I can close preprocessor and go to solution, solve current ls, OK, and solution is done. Now let's go to general post process, plot results, contour plots, and nodal solution. Let's see how temperatures are changing. So the temperatures are changing quite differently from the example in the previous lesson. In the previous lesson, everything was pretty consistent, or the lines were all vertical. But here, the temperature of 100 is more, or it takes more room in here in the bottom left corner of my model. And let's see how thermal heat flux is in x direction. So it's not like yesterday, as there was a constant 800 heat flux through x direction. Actually, here you see there is a negative value, which is pretty small, but still in the bottom left corner we have a negative value. And if I want to see the vector form of the heat flux, this is going to be this form of the heat flux. And because I insulated the top line, which means there's no heat flux to the top side of this model, the heat flux on the very top of the model is pretty parallel to the horizontal, or in x direction, while heat flux in the bottom is more towards topwards, and as it moves to the right, it becomes more and more horizontal, or in x direction. The other thing that I might be interested in is let's go to list results, nodal solution, and nodal temperatures. So temperatures for each and all of the nodes are shown to me, and so they're pretty different from the example in lesson 2. And this, I guess, concludes this lesson 3, a very basic example, again, a 1D heat conduction with heat generation.